Venus, our closest neighbor in the solar system. Known for its extreme conditions, temperatures of this planet can go up to 470 degrees Celsius, and surface pressures more than 93 times that of Earth. So how could anything man-made survive these harsh conditions? Enter the VENERA program. In October of 1967, VENERA forced entry vehicle detached from the bus on approach to Venus. Due to the constraints of the launch vehicle fairing diameter, the ballistic coefficients of the entry vehicle had to be high when using rigid aeroshell technology. In order to maximize the science payload and minimize the thermal protection system's mass, VENERA 4 had to have a lower total heat load. Hence, the vehicle had to enter the atmosphere at a steep angle of 78 degrees. This steep entry angle and high ballistic coefficient caused the vehicle to experience 300 Gs of loading when it decelerated from 11 km per second to about 220 meters per second. Also, it was known that sharp-nosed vehicles were destroyed by highly localized heating due to the formation of an attached shockwave. Therefore, VENERA 4's entry vehicle was spherical, as the use of a blunt body creates a detached shockwave. This disperses the heat over a larger volume of air and away from the vehicle. To deal with the remaining heat, an ablative heat shield made of phenolic epoxy resin was used. This works because burning absorbs heat energy through phase change and also injects gases into the boundary layer, which reduces the convective heat transfer to the vehicle. To further decelerate, parachutes were deployed in 2 stages. The vehicle's descent lasted for 93 minutes, where it got crushed by the dense atmosphere before it could land on the surface. Fast forward to 1975, VENERA 9 was massively redesigned to be larger and heavier. Proton's larger fairing volume allowed VENERA 9 to enter at a much shallower angle. This could be done because the lower ballistic coefficients of VENERA 9 led to lower heat loads at the same entry angle. Also, a better thermal protection system could shield the spacecraft from larger heat loads caused by shallow entry. This included using phase change materials that absorb heat energy, circulating fluid to direct heat away from sensitive electronics, and pre-cooling the entry vehicle to -10 degrees Celsius. After the lander descended through the cloud sheet, the rest of the deceleration was achieved with the aerodynamic shield. This was possible because the atmosphere in Venus is very dense. A torus shell placed at the bottom of the lander deformed during impact, thereby absorbing the energy and providing the upright position during landing. Shortly after, the first ever picture on the surface of another planet was taken.